Welcome to the Unit 13, Section 1 video on identifying functions from multiple representations. Through the units of this course, we have gone over many different function types, including linear, quadratic, and exponential functions. Now what we're going to do is pull it all together in this unit, and we're going to start comparing the different function types. So there's not going to be a lot of new material in this unit, but there is going to be a little bit of a different look at some of the material that we've already done. So look at the tables and graphs below. The data show three ways you have learned that variable quantities can be related. The relationships shown are linear, quadratic, and exponential. So here are those data. You can see in the first part of this table, we have the training heart rate for someone of a particular age and the number of beats per minute. And you can see a linear regression here where that linear pattern goes down. For quadratic, you have a height of a volleyball as it's in the air at various points in time. And you can see that that is a little bit more quadratic looking on the graph. And then you have a volleyball tournament, which here is represented in an exponential form. And you can see that fairly clearly by the graph. In the real world, people often gather data and then must decide what kind of relationship, if any, they think best describes their data. So in example 1, we are going to graph the data set and determine which kind of model best describes the data. So here we're given some time and bacteria. So we're going to go onto a graph, we're going to plot the data, and then connect those data points. And what we see here when we connect them is it looks like an exponential function. So the data here appears to be exponential. In this example, we're going to graph the data set and determine which kind of model best describes the data. So here we have degrees Celsius versus what the degrees are in Fahrenheit. So if we plot the data, you can see a more linear relationship between the two pieces of data. Another way to decide which kind of relationship, if any, best describes a data set is to use patterns. So if we take a look at a linear set of data in a table, we look at our y values, and we see that you can add 1 each time in this table, so we have a constant first difference. In a quadratic, you're going to be looking at the second differences, and if that's constant, it's quadratic. And then in an exponential, if we have a common ratio or a constant ratio, then it is an exponential function. So we have learned all three of these independently, but now we can start comparing the different types of data. And one way to kind of give away an exponential is you look at the y values. If they're increasing rapidly, then chances are you have an exponential and you'll want to look for a constant ratio. So let's look for a pattern in this data set to see which kind of model best describes the data. So in the x values, we're adding 100 each time. In the y values, you can see we have a decreasing amount. So let's explore and see what we have in terms of, is it a constant first difference? And here, it does not appear to be a constant first difference. So let's look ahead to the second differences. And here, the second differences are common. So since we have a constant second difference, this is a quadratic function. For this example, we have the value of a car. And over time, the value of the car goes down. The x values are constant because we're looking year to year. But as we take a look at the y values, we are multiplying each one by 0.85. Now, how do we determine that that is our constant ratio? Well, you can take 17,000 and divide it by 20,000 to get 0.85. That's what your calculator would give you. Then take 14,450 and divide it by 17,000 to also give you 0.85. And then take 12,282.50 and divide it by 14,450, and you will again get 0.85. So we do have a constant ratio, which means that the data appears to be exponential. You have studied different types of functions and how they can be represented as equations, graphs, and tables. Below is a review of the three types of functions and some of their key properties. So let's talk about equations and graphs. For a linear equation, you have y equals mx plus b. So for example, y equals 2x plus 1. Your 2 is your slope. Your 1 is your y-intercept. M is slope. B is y-intercept. For quadratic, you have ax squared plus bx plus c. So for example, x squared minus 2x plus 3. And in an exponential, you have y equals ab to the x. For example, 0.5 times 2 to the x. In a graph, a linear function is going to be indicated by a straight line. A quadratic will have a parabola, and an exponential will have some rapidly increasing or decreasing curve. In a table format, you'll have constant first differences in the y for a linear, constant second differences in the y for quadratic, and a constant ratio for an exponential. So let's identify the following functions as linear, quadratic, or exponential. So in A, we have an x in the exponent, so that would be exponential. In B, we have a x squared in there, so that would be quadratic. For C, we have slope-intercept form, y equals mx plus b, so that would be linear. For D, we have a straight line, so that's linear. In E, we have a parabola, so that's quadratic. In F, we have a curve that's rapidly increasing, so that's exponential. In this table, we have y values that are increasing by 10 each time, so it's linear. In this table, we have y values that are multiplied by 2 each time, so it's exponential. And in this one, if we look at the first differences, no pattern is here, but if we look at the second differences, we have a constant second difference, so this is quadratic. In this situation, you drink a beverage with 120 milligrams of caffeine. Each hour, the caffeine in your system decreases by 12%. Since we have a starting value and we have an amount, a multiplication factor in which it's decreasing, this is exponential. For babysitting, Nicole charges a flat fee of $15 plus $10 per hour. So an initial amount of $15 plus $10 for every hour, which is the constant amount, so that makes it linear. And then the formula for throwing a baseball in the air is represented by this function. Well, we can just look at the function here, and we know that the shape of a ball being thrown in the air is a parabola, so this is quadratic. Recall that the rate of change is a ratio that compares the amount of change in a dependent variable to the amount of change in an independent variable. It's our y2 minus y1 over x2 minus x1. In the case of a linear function, it's our slope. A function is a linear function if and only if the function has a constant rate of change. The graph of such a function is a straight line, and the rate of change is the slope of the line. So in other words, no matter where you go along the graph to pick points, you're always going to end up with the same rate of change. So let's explore that with this example. Let's take a look at 3 different intervals, starting with 0 to 15. We're going to pick our point at 0 and our point at 15, and we are going to use our formula. We'll do it from 15 to 30 as well, and we'll also get the same change in y over change in x, 8,000 over 15. And then from 30 to 40, we'll do that as well and get 8,000 over 15. Now, we could reduce 8,000 over 15, but we don't really need to here because we're not looking for what the rate of change is itself. We're just showing that it's constant. So as long as all 3 are 8,000 over 15, chances are we have a linear function. Let's look at it in a table. Here we have values that are increasing by 10 each time, so it should be linear. Let's take a look at 8 to 10. We get our x's and our y's, and we get 10 over 2. If we go from 2 to 6 and get our x's and y's, we get 20 over 4, which both of these reduce to 5, okay? So in some cases, you will need to reduce just to show us the same number. But since our slope is 5, or our rate of change is 5 from 8 to 10, and it's also 5 from 2 to 6, chances are what we have is a linear function. Here in C, we have an equation, and we're going to look at 1 to 5, and we're also going to look at negative 3 to 0. So we're going to plug in our 1 and our 5 into our equation to get 3 and 11 for our y's. Put it into our rate of change, we get 8 over 4, which is 2. We'll do the same for negative 3 and 0. Plug in negative 3 to get negative 5, plug in 0 to get 1, and we get our average rate of change using those 2 points as negative 6 over negative 3, which is also 2. So since our rate of change is 2 over different intervals, then chances are we have a linear function. And of course, the more different intervals that you check, the more your certainty starts to increase that these are linear functions. You may want to do it over not just 2, but maybe 3 or 4 different sets of points to see if you get the same thing everywhere. A function with a variable rate of change is a nonlinear function. Examples of nonlinear functions include quadratic functions and exponential functions. One way to compare two nonlinear functions is to calculate their average rates of change over a certain interval. For a function f of x whose graph contains points x1, y1, and x2, y2, the average rate of change of the interval x1 to x2 is the slope of the line through x1, y1, and x2, y2. So, in other words, if you pick 2 points along, say, a parabola, and you find the rate of change, it's the same as the slope of the line that goes through those 2 points. Quadratic functions will have different average rates of change across different intervals. Exponential functions will exhibit a common ratio. So let's look at a quadratic function. We're going to find the average rate of change over each interval to show that the rates of change are different. So from negative 3 to negative 2, we find what our y values are, put in our rate of change, and we get 3 over 1, which is 3. From negative 2 to 0, we put in our y's that go with those x values, and we get 0 as our rate of change. So since our rate of change is different, then we know, first of all, it's not linear. So that does point to it either being quadratic or exponential. And in this case, it is quadratic. We've just shown that it does not have the same rate of change. For a table of values, here we're going to look at negative 2 to 1 and 0 to 2. So negative 2 to 1 gives us a rate of change of negative 6 over 3, which is negative 3. From 0 to 2, we find the y's that go with it, and we get 2 over 2, which is 1. Again, showing that at the very least, it is not a linear function. For C, we have an equation. Plug in your negative 2 to get your y that goes with it, which would be negative 15. Plug in your 2 to get the y that goes with it, which is 11. And then plug those into your average rate of change formula to get 13 over 2. Then from a different interval, we're going to plug in our negative 1 to get negative 8. Plug in 3 to get 0. And then plug in your y2 minus y1 over x2 minus x1. And that's going to give us a rate of change of 2. Now let's look at the average rate of change over an exponential function. So from negative 1 to 0, we have 1 minus 2 over 0 plus 1, which gives us negative 1 over 1. For 0 to 1, we have 1 half minus 1 over 1 minus 0, which gives us negative 1 half over 1. Now you'll notice that both of these are over 1, so therefore that kind of leans us toward having a common ratio since our numerators are the same and our different rates of change. In a table, we have from 2 to 4, a rate of change of 12 over 2, which is 6 over 1. For 0 to 2, we have a rate of change of 6 over 4. So again, same numerators, different denominators. Again, showing that we are not linear at the very least, but we can kind of at least start to assume that it's exponential here because we have a constant ratio. For C, we have 3 to the x So that's 3 to the 0, which gives us 1. 3 squared gives us 9. Plug that in, we get 4 over 1. From negative 3 to negative 1, we have 1 over 27 for 3 to the negative third, and negative 1 for 3 to the negative 1, which is 1/3. Plug those in, we get 4 over 27, which again shows it's not linear, so it's either going to be quadratic or exponential, and further investigation showing that it is indeed exponential. You have learned many key features of linear, quadratic, and exponential functions. Several key features can be determined for all three function types. So in this table, we're going to compare what the different function types have in common and what's different between each key feature. Starting with the x-intercept. For all three, it is where the function crosses the x-axis and is written as x0. For the y-intercept, it's where the function crosses the y-axis and written as 0y. That's going to be the same for all three function types. The domain for all three of these is the set of all x values, and for all three functions, the domain will be negative infinity to positive infinity. So whether you're given a linear, quadratic, or exponential function, your domain will be all real numbers. For range, for all three, the definition is the same. It's the set of all y values, only interval to use y values. For a linear function, it's always going to be negative infinity to positive infinity. For a quadratic, the range is going to be negative infinity to some maximum when there is a maximum value on the graph, and it's going to be the minimum value to infinity when there is some minimum on the graph. For an exponential, the range is negative infinity to the asymptote when the graph is below the asymptote, and the range is the asymptote to infinity when the graph is above the asymptote. Be sure to use the correct notation. Note that in a quadratic, we do include your vertex, so you're going to use a bracket, but in an exponential, you do not include the asymptote because you're never going to touch it. For increasing and decreasing intervals, it's the function increases where it goes up from left to right, and the function decreases where it goes down from left to right. That's the same for all three. Now let's talk about what's unique. The function is either always increasing or always decreasing for linear functions, and written as negative infinity to positive infinity. The one that it's not doing, you're just going to write none. For quadratic, it is going to be when concave up, increasing from the vertex to infinity, and decreasing from negative infinity to the vertex, and vice versa when you're concave down, increasing from negative infinity to the vertex, and decreasing from the vertex to positive infinity. For an exponential, similar to a linear function, the function either always increases or always decreases, and written as negative infinity to positive infinity. So linear and exponential are very similar for increasing and decreasing intervals. Quadratics, you're going to have one of each. For positive and negative intervals, going to operate the same way for all three. The function is positive where it is above the x-axis, where you have positive y values. The function is negative where it's below the x-axis, where you have negative y values. Where there are multiple positive and negative intervals, union them with a u. And that is going to only occur when you have a quadratic. Linear, you'll have potentially one positive interval and one negative interval. In fact, that's typically what you're going to have. Exponential functions, you will have one positive and one negative interval if your graph crosses the x-axis. But if it doesn't cross the x-axis, it's either going to be always positive or always negative. Now for end behavior, it tells what is happening to the function as x approaches infinity on the right and negative infinity on the left. Always follow this setup. As x approaches infinity, f of x goes somewhere. As x approaches negative infinity, f of x is going to go somewhere. It's always going to be formatted this way. Remember, f of x is another way of expressing the output, or y. The f of x will always approach infinity on one end and negative infinity on the other for a linear function. In a quadratic, the f of x will always approach either positive infinity on both ends or negative infinity on both ends. And for an exponential, one will always approach the asymptote and the other will approach either positive or negative infinity. There are some key features that are unique to specific function types, so let's go over those. Linear function features include slope. From a graph, you can read slope as rise over run from two ordered pairs, y2 minus y1 over x2 minus x1. For a quadratic function, you have the axis of symmetry, which is the vertical line that cuts the parabola in half. When given an equation in standard form, it can be found by the equation x equals negative b over 2a. The vertex is the ordered pair at the top or the bottom of the parabola. And the exponential function features include the asymptote, the invisible horizontal line that the function gets close to but never touches or crosses. When given an equation, the asymptote is located at y equals k. So let's do an example where we compare key features of some functions. So the x-intercept for the exponential function in the first column, we have 1, 0. For the linear function in the second column, we have 6, 0. And we have two of them for the parabola since we cross the x-axis twice, negative 2 and positive 2. The y-intercept for the first one is 0, negative 1. For the linear function, we have 0, 4. And for the parabola, we have 0, negative 4. Now the domain, remember the domain for all three is going to be the same, negative infinity to positive infinity. Now the range from an exponential, since we are increasing rapidly, the graph is above the asymptote, we're going to go from the asymptote to infinity, and our asymptote is at negative 2, so negative 2 to infinity. The range for a linear function is negative infinity to positive infinity, and for the parabola, we're going from the vertex to infinity, so negative 4 to infinity, and you include the vertex in a parabola. For the exponential function, we are increasing from left to right, so negative infinity to positive infinity. We do not increase in the linear function, and only half of the parabola is increasing, and that is from 0 to infinity. For decreasing, since we're increasing everywhere in the exponential, we are not decreasing, but the linear function is decreasing the whole time, and the parabola is decreasing where it's not increasing, so from negative infinity to 0. For the end behavior, the exponential is increasing. As we approach infinity, we're going to infinity in the y, or the f of x, so as x goes to infinity on the right, f of x goes up to infinity. As x goes to negative infinity, we're approaching the asymptote, so f of x approaches negative 2. For the linear function, as x goes to infinity on the right, is pointing down, so we're going to negative infinity. And then as we go to negative infinity on the left, we're going the opposite direction, we're going up to infinity. And then the parabola is concave up, so both ends are pointing upward, so both ends are going to infinity. Let's look at these three. The domain for the first one is negative infinity to positive infinity, same for the linear and exponential functions. The range for the first one is negative infinity to 4. The linear function is negative infinity to positive infinity. And for the exponential, the asymptote to infinity, so 2 to infinity. For the first one, we're increasing from negative infinity to 3. For the linear function, we are not increasing at all, but we're increasing everywhere in the exponential. For the parabola, we are decreasing from 3 to infinity. We're decreasing everywhere in the linear and nowhere in the exponential. For the positive interval in the parabola, that's from 1 to 5. That's where we're above the x-axis. We are above the x-axis from negative infinity to 1 in the linear equation or graph. And then for the exponential, we're positive above the entire x-axis. So the entire graph is above the x-axis, so negative infinity to positive infinity. For the parabola, we are negative from negative infinity to 1, and then again from 5 to infinity. So we are going to union those two pieces. For the linear function, it's from 1 to infinity, And for the exponential, we are not negative anywhere. For the end behavior, we're concave down on the parabola, so both ends are going to go to negative infinity. For the linear function, as we go to infinity in the x, f of x goes to negative infinity. As x goes to negative infinity, f of x goes to positive infinity on the left-hand side. And then for the exponential, as x approaches infinity, f of x goes to infinity. And then on the left-hand side, we're approaching 2. For this last example in this little section, let's take a look at some unique features. So the domain, always going to be negative infinity to positive infinity for quadratics, linear, and exponentials. The range in the quadratic, negative infinity to 4. For the linear, it is from negative infinity to positive infinity, and for the exponential, negative infinity to 5, where our asymptote is. Slope only applies to the linear function, so we're going to do rise over run. So you go up 1 and to the right 2, so that's going to be 1 over 2, rise over run. Axis of symmetry is only for quadratics, so we look at our first column here, our parabola, and our axis of symmetry is at x equals 0. Again, maximum and minimum and our value only applies to quadratics, so we do have a maximum, and that is located at y equals 4. And then our vertex is at the point 0, 4. Let's look at our exponential in the third column. For our asymptote on that one, we have y equals 5. And then one more look at all three end behaviors. We're concave down the parabola, so both ends go to negative infinity. We are on the right going up, so the right-hand side goes to infinity, the left-hand side goes to negative infinity. And then with the exponential, the right-hand side goes to negative infinity, the left-hand side goes to 5. Recall, a parent function is the simplest function with the defining characteristics of the family. The linear, quadratic, and exponential parent functions are listed here. So you have y equals x for linear, y equals x squared for quadratic, and y equals b to the x for exponential, where b is some base. It could be 2, it could be 3, it could be 1/2. It's whatever your base is. And there's our transform forms. We have a, h, and k in all three of those, and they're all in the relative same location. Any function that is translated, reflected, stretched, or compressed is a transformation of the parent function. Notice the similarities of where the transformation variables are located within each function's transformation rules. The a is always out in front, the h is always followed by the x, and the k is always sticking out on the end. So if you know how to transform one function type, you know how to transform any function type, or at least you can identify them. So let's list through the transformation and look at the rules for all three. Horizontal translation to the right is when h is positive, so you're going to follow that with a minus some number behind your x. Horizontal translation to the left is when h is negative, so it's going to look positive in all three cases. Or a vertical translation up is when k is positive. So in all three cases, you're going to stick some positive number on the end of your function. Same thing with a vertical translation down. You're going to subtract some value on the end of your function. Reflection across the x-axis occurs when a is negative, so you're always going to look for a negative sign out in the front of your function. A reflection across the y-axis always occurs when x is negative, so that negative will be in front of the x. Notice that you have to have the parentheses on a quadratic or an exponential for that reflection of the y-axis to occur. For a linear, a reflection across the x is the same as a reflection across the y. A vertical stretch occurs when a is greater than 1, so you're going to have some value greater than 1 in front of your function. And a vertical compression happens when a is between 0 and 1. So you'll have some value between 0 and 1 in front of your function. So let's identify the transformations that take place in each equation. So here we have a linear function. We have a negative out in front, so we're reflected across the x-axis. The 4 tells us that we are stretched. The -1 behind the x tells us that we're translated right 1 unit, and the +3 on the end tells us we're translated up 3 units. Here in this quadratic, we have a 2 out in front, which tells us we're stretched. We have a +9 behind the x, which tells us we're translated left 9 units. And we have a +6 on the end, which tells us we're translated up 6 units. In this one, we have a minus out in front, which tells us we're reflected across the x-axis. We have a vertical compression of 1/2. We have a +2 behind the x, which tells us we're translated left 2 units. And then a -7 on the end tells us we're translated down 7 units. Let's identify some transformations based on the graph. The thin function is going to be the parent function. The thick one will be your transform function. So let's take a look at this linear function. So remember, linear functions are a little bit more basic. So we're looking at the slope and the y-intercept. And here the y-intercept moved up 5 units. So this is translated up by 5. But our slope did not change. So that's our only transformation. And our equation is y equals x plus 5. For this one, we have a change in our slope and a change in our y-intercept. So our slope became -3/1, which is -3. So that's a vertical stretch of 3, and we're reflected across the x-axis. So that is indicated by our negative slope. And we are translated up 3 units because our y-intercept went up 3 units. So our equation is y equals -3x plus 3. Now let's look at some quadratics. Here, we're clearly reflected across the x-axis. And if we take a look at the curve, you can tell that it's a little bit compressed. The vertex didn't change, so our h and k didn't change, but we are compressed. So if we look at our parent function, if you go over 2, you have to go up 4 because 2 squared is 4. But in our transform function, if you go over 2, you go down 2. 2 is half of 4, so we're compressed by 1/2. So our equation is going to be -1/2 x squared. For this quadratic, we're not reflected, and it doesn't appear that we are stretched or compressed, but we are translated. The vertex moved to the left 3 units and down 4 units. So our h and k values changed, so we have x plus 3 quantity squared minus 4. Now let's take a look at a couple of exponentials. Here, we shifted our asymptote up 3 units, so our k moved up 3 units, but it doesn't appear anything else happened. So we have 2 to the x plus 3. For this one, we reflected. That appears to be the only thing that occurred, so we're going to put a minus sign in front, -2 to the x. Thanks for checking out my video in the Algebra 1 Honor Series. You can subscribe to my channel. I've got the next video queued up for you, and if you need to check out any of the videos in the course, I've got the course playlist for you here as well. Thanks for watching.